everyone! So in this video I wanted to review some of the properties of water that are important for life. So we really need to start with talking about the polarity of water and how that relates to hydrogen bonding. So first we need to really look at the chemistry. Water is made of covalent bonds that form between one atom of oxygen, and remember oxygen is highly electronegative. So that means that this element tends to hog electrons. And then the two atoms of hydrogen are actually happiest without their electrons, so to speak. I'll explain. So oxygen normally has 6 electrons, which are represented by the red dots here, 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 and here. So we have 6 electrons that normally come with the oxygen. So it's really important to understand that electrons are not married to their atom. They are free to float around different atoms, come back, they swap places with one another. So in covalent bonding, we actually see that the 2 of the electrons from oxygen and 1 electron from each of the hydrogens should be shared. That's a covalent bond, sharing of electrons. But with oxygen being more electronegative, actually these electrons spend more time with the oxygen than they do with the hydrogens. So a lot of times in nature we see hydrogen existing as H+. So it just kind of chills out as H+. And so if we look at that, that plus is indicated because this hydrogen contains only 1 proton. So if we think back to the octet rule, oxygen actually has 6 electrons, so it needs 2 more electrons to fill the octet. So most of the time these electrons are going to chill out around oxygen so that it can fulfill the octet. Hydrogen, though, typically likes to be positive. It has just a proton and a neutron, and a lot of times it just lets its electron go loose into the world. And this is going to be really important when we talk about acids and when we talk about photosynthesis and cellular respiration in later lessons. So keep that in your brain for later. Okay? But because these electrons, the 2 extra electrons, hang out more around oxygen, oxygen ends up having a partially negative charge. So this symbol here is delta, and I'm not very good at drawing it, but this means partial negative. Okay, so we end up having 2 extra electrons hanging out around oxygen most of the time. And then our hydrogens, because those electrons are pulled away, they are going to be partially positive. Okay, so this is really important because it makes water polar. So this is a polar covalent bond, in which case the electrons are not shared evenly. So we have a negative pole and we have a positive pole. And this allows water to engage in hydrogen bonding. So I'm going to represent that by a dashed line. Okay. And the reason why I'm representing the hydrogen bond with a dashed line compared to the covalent bonds with solid lines is hydrogen bonds aren't quite as strong as covalent bonds. But altogether, a whole bunch of hydrogen bonds, when you start adding in other molecules, are going to be very, very strong. And this is going to give water a lot of the really cool properties that we're going to talk about in this class. The next thing that I want to talk about related to water actually has to deal with how hydrogen bonding occurs in a bunch of water. So if you have a lot of water, like a large body of water, a lake, you will see that water on a molecular level actually kind of makes a lattice structure. So you have a bunch of water molecules all hydrogen bound together. So before we get into this and how this relates to a high heat capacity, I want to back up a little bit and talk about density because that's not something that we really go into heavily in class, but it's going to be really important for understanding why water doesn't freeze solid throughout the winter, and also it'll be important later when we talk about weather and climate and how air circulation occurs throughout the globe. So when we are talking about density, density is equal to mass divided by volume, or how many molecules are in a given space. So if we were talking about these 2 circles, let's say that I had a ball of air in my hand and I'm representing this. So if the air would be less dense, there would be just a few molecules in that area of space. and then more dense would represent more molecules getting crammed into that same area of space. So this is going to be really important when we start talking about temperature. So typically molecules are constantly in motion, unless even when they're in the solid state they're moving, but they're just moving a lot more slowly. So as molecules heat up, they move faster and they start colliding off of each other. So air, for example, would actually be less dense when it is warm because the molecules are bouncing all over each other and they're moving away from each other. And then air, as it moved closer together, would become more and more dense, okay? And so this will be really important later on when we are talking about rain and the water cycle. But for now, I want to try and relate that back to water and why water doesn't freeze throughout the winter. So here I have diagrams of water and how far spread out the hydrogen bonds are depending on the temperature. So water is actually most dense at 4 degrees Celsius, which means that the hydrogen bonds are squished down as small as they can possibly go. And so we would see that here. We'll say that this is about 4 degrees Celsius, and this is the most dense. So typically we actually see cold water sinking down to the bottom, and the water, warmer water would stay up at the top. So if you think about the concept that hot air rises, then we have heat rising because hot air is less dense, so the molecules are more spread out, and then cold air sinks because the molecules are more compact together. And that's kind of the same thing that we would see here. The most dense water is going to be at 4 degrees Celsius. So above 4 degrees and below 4 degrees, but not quite 0 degrees yet, water actually kind of relaxes a little bit. So this would be, we'll just call it plus 4 degrees Celsius, but it's also that little margin below 4 degrees, but before freezing. So here, the water molecules can actually spread out a little bit more, and the farther spread out that the molecules get here without, as they get warmer, the more likely they are to break apart, and we'll talk about that a little bit when we talk about evaporative cooling. So as these molecules spread out and the hydrogen bonds get stretched, as heat increases, we can actually go into evaporation. However, freezing at 0 degrees Celsius is actually when we see, as far as getting colder goes, the farthest that those hydrogen bonds are spread out. So this is actually very low density compared to 4 degrees Celsius or liquid water. So these two here are actually liquid water. And then this would be ice. Okay. So the reason why ice floats is actually because the hydrogen bonds are so spread out that water is very not dense, and so it's going to float on top of the warmer water below. Water also has a very high heat capacity. So because of all of these little hydrogen bonds, there's a lot of heat energy stored inside the molecules of water. So as the temperature of air drops, water actually stays relatively warm compared to the land and the air outside of it. And so as the top of the surface starts to freeze because of making contact with that cold air, what you end up is actually getting a barrier. So ice creates a barrier which is going to protect the water below from the cold air above. So now you actually have all of this heat energy being trapped in the liquid water below the ice, which allows the lake to remain liquid. And then life can continue throughout the winter despite the fact that the air and the ground outside of the water can be pretty solid. It's also important to understand that in the summer, the water temperature is not going to rise very quickly. So water will stay cool for a relatively long time compared to how quickly the air and the ground heats up. Now, it's not to say that water won't heat up, and it's definitely not going to stay freezing for very long, but because of all of the energy that is trapped there, it maintains a relatively constant temperature. So typically, while the ground around the water can go anywhere from 0 degrees Celsius to 38 degrees Celsius, so from freezing to like 100 degrees Fahrenheit, the water below may only change about 10 degrees throughout the year. So the top surface of the water is going to warm up more quickly, but remember, heat rises, so that hot water is not going to sink So you're not going to get a lot of mixing of the cooler water below and the hotter water above. So what we end up seeing is that the temperature stays relatively cool throughout the entire year. Now this is of course going to vary by the size of the water body. Smaller water bodies have less water molecules and they're going to be more subject to temperature change, but larger bodies of water are not as subjected to that compared to maybe a pond or some smaller lakes. The next important quality of water that has to deal with life is having a high heat of vaporization. So essentially this goes back again to the hydrogen bonding and also to the high heat capacity of water. So because water changes temperature very slowly, it actually takes a lot of heat energy in order to get the molecules of water moving fast enough where they rip apart from one another, or they break, so we get those hydrogen bonds breaking, and that's what's called evaporation. So when we are looking at water normally, let's just say that this is our cool water, right? So as water warms up, those hydrogen bonds start to spread out even farther, and eventually with enough energy put into the system, the hydrogen bonds are going to break, and then the water molecules are released as a gas into the environment. Now this is really important for living things because this is involved with cooling. So these hydrogen bonds, when they break, they actually pull heat energy from the surface of the system. So if you think about a plant leaf in the heat of the summer, the leaf is actually giving off water. So that allows the surface of the leaf to cool through evaporative cooling. Same thing when humans and other mammals sweat. So that sweating process allows the heat to break and get pulled away from our skin so that we can cool down on a hot day. And the last of the really important properties of water that I wanted to talk about in this video is the purpose of adhesion and cohesion. So because of the hydrogen bonding, water molecules can stick together. So when we're talking about adhesion and cohesion, we're talking about the ability of water molecules to actually stick to each other, as well as the water molecules being able to stick to other polar surfaces, such as the inside of your blood vessels. So the inside of your blood vessels is actually polar, so that allows for the cohesive properties of water to allow the water molecules to stick together, and then the adhesive properties where the water molecules can actually stick to your blood vessels and pull their way through your blood vessels. And this is also really important for large trees and other plants outside because they can't get up and move, they can't drink water, so they need to be able to get water from the ground up into their leaves so that they can do cellular respiration and use the energy that they've created from the sun in the form of sugars to break that down into cellular energy, which is ATP. So they have xylem, which is similar to our blood vessels in a way, as this allows them to move water up from the ground through their stems and into their leaves. And so the water molecules stick together, and so if you think about it, xylem kind of acts like a straw. At the surface of the leaves, an evaporative process called transpiration is occurring. So water is evaporating at the surface of the leaf, which is actually helping allow the leaf to cool down, and essentially the whole plant can cool down that way. And then as the water leaves from the surface, that kind of creates a suction like a straw, so that can pull more water up through the plant. And so you actually have evaporative cooling going on, and then you have adhesion and cohesion, allowing that water to move up into the plant. I wanted to talk about the properties of water and the properties of soap as related to how you can actually get things clean. So we've talked about how water is polar, and things like oil and dirt are actually hydrophobic. So they don't like to interact with water. So we call hydrophobic water fearing because these molecules are going to be resistant to being lifted up by water, and they don't really mix with water. So if you've ever had a glass of water and had oil on it, you'll notice that the oil actually floats. So here, let's say we have some oil and some dirt and we have some water and really nothing's going on. Maybe you just made some pepperoni pizza and you want to clean the pan clean. Hot water sometimes does the trick, but you'll notice that there's still actually a oily residue on the pan. So what you want to do is add some dish soap. So dish soap is actually made with a fat and a salt. So the fat is going to be really important because you have these fatty acid tails. And the fatty acid tails are going to lock in with the oil and the dirt. Okay. And on the other end, the head, you have a salt. And so the salt is going to actually be polar. So you have the head of the soap is actually going to interact with your water, and it can create hydrogen bonds that way. So if we look at the anatomy of a soap molecule, you have your polar head, and then you have a non-polar tail. Oops. And this is actually going to be similar to the phospholipids in your cells that make up your phospholipid bilayer. So make sure you pay attention to that. They work very similarly. So in your body, and when your cell membranes are forming, the nonpolar tails, which are hydrophobic, are going to flip to the inside away from the outside and the inside of the cell, and then the heads are going to be interacting with the water. So the same thing is occurring here with soap. So you have your fatty acid tails associating with the dirt and the oil. So the fatty acid tail is nonpolar, so that is hydrophobic. And then you have your polar head, which is hydrophilic. And this is going to be able to interact with the water. So you end up with your hydrogen bonds forming. And now the water can associate with this complex, which is called a mycel. So now you have this mycel forming, which is kind of like a glob of your soap surrounding the dirt, and then the water can lift the dirt and the oil off of your the surface, such as your pan, and you can wash those away.